All right, so for part two, this is the third one I'm doing, but this is the second one for you. What I'm going to do is I'm going to put an electron right here, E minus, and that electron has an electric charge minus E, which is minus 1.609 times 10 to the minus 19 coulomb. And it's going to have the same setup, the 20 by 20 plates and the plus or minus 10 nanocoulomb charges as before in the previous example. So this delta V is equal to 112.5 volts, like we just found. And what we want to do now is to figure out what happens if I place this electron here with zero speed next to this negative plate. How fast is it going when it hits this positive plate? Okay, so we want to figure that out. And the way we do this is through conservation of energy. Now, since we've already found the potential difference, we call this 0 and this 112.5 volts, then the energy here, the amount of work done, is going to be equal to that charge minus E times the delta V. All right. And remember, this is minus 1.60 something or other times 10 to the minus 19, and this is 112.5 volts, 1.602. All right, and so that's what we need to do, is we need to say, okay, what is the kinetic energy at the beginning, the potential energy at the beginning, and then figure out what the final kinetic energy is plus the final potential energy. This is the final potential energy here. The initial potential energy we just said is 0, right? This electron is not moving, so it has no kinetic energy. So the initial is 0, and the final kinetic energy is 1/2 m, we'll call that mev squared. I don't know if I did that or if I just called it m, which is the mass of the electron, plus this minus E, the charge of the electron, times the change in the potential between these two positions. Okay, so that's how we're going to start. And once we have that, now we're in a situation where we can start plugging these numbers in. Now we have to look up that mass of the electron. That's going to be 9.11 times 10 to the minus 31 kilograms. That is considered relatively light, times the square of the velocity. It's going to equal this, because this is negative, we turn it into positive, put it on the other side, so that's 1.6. Got to put 1.609 here. I think it's 1.602 times 10 to the minus 19 coulombs times 112.5 volts. Okay. We multiply all that out, we end up with 181 times 10 to the minus 19 volts times coulombs. All right. And a volt times a coulomb is a joule. And here we have 1/2 of 9.11, so that's 4.55 times 10 to the minus 31 kilograms times V squared. So then we have to divide through by the 4.55, so that's too hard. That's a little less than 4, maybe 3, so 39.8 maybe, times 10 to the 31 minus 19 is 12 joules per kilogram. And a joule per kilogram is equal to meters per second squared. Okay, so then we take the square root of that. We get a number which is 6.31 times 10 to the 6th, is a 12 meters per second. And that is the speed when it gets there, which is considered relatively quick, right? So your electron comes down all the way down here, and it has a speed that's greater than 1,000 kilometers per second. I mean, assuming this is vacuum. And it's not hitting anything. If it starts hitting things, then all bets are off. It's going to stop and slow down and move in this direction, that direction, will slow down. But if that's a vacuum and there's nothing in between, it will speed up in a real big hurry. Remember, that's only 5 centimeters. All right, so basically what we do here is, in a situation where we can use the potential, we can use conservation of energy, right? Conservation of energy takes the same form it did in the previous course. You sum the initial kinetic and potential energies, and those are equal to the sum of the final kinetic and potential energies. And that lets you put things together. In this particular case, we defined this as 0 and this as 115 or 112.5 volts from the previous example. It would be just as easy to do this as minus 112.5 volts, and this guy is 0. You'd end up with the same thing. As long as you make sure you use that minus sign for the E. After that, it's just plugging the right numbers in. Had to look up the mass of the electron, which is 9.11 times 10 to the minus 31 kilograms. And you have to look up the charge of the electron, and this we brought in from a previous problem. Not episode, problem. All right. So that is how to do this one, and I will talk to you in about 30 seconds. Bye now.